So saying thank you very much for the invitation. I'm so happy to see we have almost 40, 50. We have 50 people in the webinar right now, which is amazing. It's I would never get this chance to meet so many people under other circumstances. So I hope that this sets a I hope that there is a positive outcome of the current situation of having much more global interaction, because this to me is has tremendous potential for communication, for interaction, for meeting new people, and this kind of thing. So thank you very much for the invitation. So actually there are two, as I was mentioning a moment ago, there are actually two Sharif alums who participated in the talk I'm giving today. One is Mohammed Javad Azizi, who is I think in the webinar right now. He's working with me at USC, working on a very difficult problem, and he's actually doing his qualifying exam on this topic next week, and so he knows these slides very well. And the other is Mehdi Barouzi, who was my former student at University of Minnesota, and now he's at Northeastern University in Boston. And so I am going to talk about a field of research called the continuous approximation paradigm, or continuous approximation models. And this is a way of studying transportation and logistics problems that is not it is not very rare, although it is not it's not the primary way that we as operations researchers tend to study these sorts of problems. So there's some interesting theorems and interesting results that you can prove by looking at problems in a certain way. So Carlos de Gonzo is in the or was, I think he's retired. It comes from the civil engineering department at UC Berkeley, who is regarded as one of the big sort of founders of this field. The idea is that you replace, I have a quote here, you replace detailed data with concise summaries, and numerical methods are replaced by analytic models. And so the idea is that you have a logistics problem that you're interested in studying, and you break it down to the simplest possible model you can by eliminating any extraneous information and simplifying assumptions, like saying, oh, pretend my distances are all Euclidean, or an L1 norm, or something easy like this, or I assume that all of my demand follows a probability distribution, or something to that effect. And then the goal is that we prove some kind of theorem about the behavior of this problem, maybe in an asymptotic limit as the amount of demand becomes large. And I like to think of a comparison here with what is called the technique, what's called Fermi estimation, which maybe some of you have ever done this before. A lot of people have done this kind of exercise, but they don't refer to it by name. And Fermi estimation is this idea. In the US, they often teach this when you learn physics. They like to explain it in this context. So Fermi estimation is a technique where you try to estimate a number just by using very basic data. And you don't want to get the number perfectly, but you just try to use sort of common sense to get the right order of magnitude. And so this is a famous example here, is you ask, how many piano tuners are there in Chicago, right? A piano tuner is the person that opens the piano with a wrench and fixes the strings. And so I don't know that information, right? I could Google it nowadays. I could search for it, but pretend I don't have that information. I don't know it. I just want to guess. And I'd say, well, okay, what are some things that we do know? We know that Chicago has a population of about 3 million people. And we'd say, okay, so an average family has 4 people in it. And so there are 750,000 families about. And if 1 in 5 families has a piano, then that means you'd say 150,000 pianos in Chicago. And if the average piano tuner worked on 4 pianos every day, which is, it's we don't know if it's 4, but it's more than 1, and it's probably less than 40. So, 4 seems like a good number. And they rested on weekends and had a 2-week vacation during the summer, then the number of pianos that they would tune is 150. Then the number of pianos they would tune is 1,000. They'd get 1,000 pianos in a year. And you'd say, okay, well, divide these quantities out in the appropriate way. And you'd say, okay, there's about 150 piano tuners in Chicago. And if you Google it, there's about 300. So we're off by a factor of 2, but for rough estimation, that did a pretty good job. And in my opinion, the continuous approximation model is this same kind of principle, but instead of asking questions about piano tuners, we talk about the length of a VRP tour or a traveling salesman tour or things like that. So this is a famous theorem. In my opinion, this is the first theorem in this field. It's called the Beardwood-Halterd-Hammersley theorem. Actually, no, there's one that predated it even further from 1955, but this is very early. This is from 1959. And it says if you have a sequence of independent uniform samples on a compact region R in the plane, then with probability 1, the length of the TSP tour divided by the square root of the number of points is equal to a constant, which we know is between 0.625 and 0.9204. And what this says is that we can approximate the length of a tour as this constant times root n. And so this is where I'm going to share my screen for the first time. I'll share my my whiteboard first. So what does this theorem say? We can think of it like this. You take the unit square, and you take n random samples. Okay, n random. We'll say uniform samples, and you take a TSP tour. And so that would look like, like that. Okay, so we take this TSP tour, and now we'll plot the length of the tour as a function of n. Now, of course, this is random, so it, that quantity is it's going to vary, but we'll disregard that, and we'll just ask how this. Obviously, this is an increasing function because you add more points, the TSP tour gets worse. And so this theorem says, well, what kind of shape does this curve have? And this theorem says that this curve, with probability 1, it basically that it looks like this constant beta, which is about equal to 0.71 times the square root of the number of points. So what I now have is I have a way of predicting the length of a TSP tour with what turns out to be a pretty good degree of precision, without actually computing the tour. And now I'll use MATLAB to show this principle again. So now I'll share my entire desktop here, and like that. And we'll bring this up. So this is there. So what I did is I took a plot here. Hold on, plot x. Just to make sure you can see the points, just so I make my message clear. So what I've got here is a TSP tour of, I think this is 500 points in the unit square. So the TSP tour of 500 points. And this theorem tells me that if I want to predict the length of this thing, what I do is I take the square root of the number of points, which is, I've written that as n is the variable here, that's 500. And you multiply it by this constant, which, as I said before, we know from experimenting is about 0.71. And so this is my prediction for the length of this tour, 15.876. And then I'll actually compute the tour. And what do I get? I get 16.56. So I'm off by, less than 10% for 500 points. So it's an asymptotic expression. There's some error there, but that's to be expected. And so that's what this theorem, it's called the BHH theorem for Beardwood, Halton, Hammersley, which were the 3 authors of this result. And so this is to me the best example of a theorem in the continuous approximation field of study, because that's what it does, right? I didn't actually have to compute. I computed the TSP tour there when I had MATLAB open, just so you could see it, but I can make that prediction without doing this. And so it's natural to ask how these kinds of theorems generalize. So for example, non-uniform distributions. The same theorem also has an equivalent when you have a non-uniform distribution. The difference between the non-uniform and the uniform case, if you look at the right-hand side of this expression, is just that you have the same constant that you multiplied before, but now you also multiply by this integral. It's an integral of the square root of the density. So the proof of why that is the case is a little long, but I'm just going to state that. So now if you give me a non-uniformly distributed points and take their TSP TOR, we can now predict the length of that TOR by computing this integral. This also works in higher dimensions. Let's see, this is in RD. We're only going to look at R2 today. We're only going to do the plane, so this is not so relevant for us, but I'll include it there anyway. There's a D-dimensional case, and then a D-dimensional case with non-uniform distributions. And again, this all goes back to, I think, 1959. I think they covered all of these cases back then. So I should say these kinds of theorems also exist for minimum spanning tree, for non-bipartite matching, so for general matching. This kind of statement holds as well. And even for things like the length of a Voronoi diagram or a Delaunay triangulation. So lots of quantities satisfy this. Dorrit Hochbaum at UC Berkeley and Michael Steele at the Wharton School proved a theorem of this kind in the 1990s for the K-medians problem, or I guess I should say P-medians problem is what I'm calling it in the text there. They proved this kind of square root law works as well for the P-medians case. And I'm going to elaborate on why this one is important for us as well. Oh, P-medians, by the way, just in case you don't know what that problem is, I'll just sketch a quick picture of it here so you can see it. The P-medians problem looks like this. You're given a collection of points like this. You have n points. And P is you're allowed to select P-medians out of these P medians, which means I'm allowed to, so let's say n is equal to whatever number that is. That looks like 11 points, and P will say is 3. My goal here in the problem is to select P points there. So this is 1, this is maybe up here, looks good, and then maybe this one. Select these 3 points to minimize the sum of all of the other points to their nearest median point, like this. So it's a facility location. It's facility location with a hard constraint on the number of facilities that you're building, and with no opening costs. So that's all that is, and we'll refer to that in a moment for one of the theorems I want to talk about. So having said that, I'm going to talk about. Let's see. I guess I'll do this really quickly here. It's I want to make sure I don't go over, but I think this is probably valuable. So a natural question is, how do you come up with this? Where does this square root come from, right? Why does the length of this TOR look like the square root of n? And I would say to look at the following picture here. So let's say we have some points in the unit square, and we're going to generate a TOR that visits all of these points whose length does not exceed square root of n. And so the proof techniques will work like this. What we're going to do is zigzag back and forth with this path here. We're going to zigzag back and forth in this square m times, where m is a variable that's under my control. Okay, so bigger m, of course, means moving around more, right? Zigzagging back and forth, and that path is longer. So we'll zigzag back and forth like that, and then we'll take little detours to that zigzag TOR to visit these additional points. And so the bigger m is there, the smaller these little detours are. You see the little additional work I have to do to go from the path to those points there. You can see that gets smaller. And so the optimal value of m as n becomes large is that it looks like a square root of n. And so therefore you've proven that if I build a TOR in such a way that the length of the total TOR in the asymptotic limit looks like 2 times square root n. And then I have a plus 2 there, but of course we can get rid of that. That goes away in the limit. Okay, so that's an intuitive reasoning for why this square root would appear. And I haven't proven any of these theorems, I've just stated them, but I hopefully that's enough to convey some of the techniques here. Now let's talk about, there's 2 problems that I want to talk about today. 2 problems I want to talk about, which is that we're going to try to prove theorems like this BHH theorem But instead of for TSP, we're going to look at, as I said in the title, some sort of modern logistical problems, or logistical problems that are a little less conventional. And so the first one of these is called sidekick routing. And a sidekick routing problem is a term that I'm using here. We have a paper here where we call it a horsefly problem, which is the same thing. The idea is that you have, it's a routing problem where you have a large vehicle like a truck, and that large vehicle acts as like a base point for some smaller vehicles. So in particular, I would say to look at the lower left picture here. This is a Mercedes van called the Vision van. And it's an electric van that has 2 drones on top of it. And so that van drives through the city or the neighborhood, and these drones pick up packages from that van and drop them off at people's houses, and then they come back to the van and pick up more things. So the lower left is an example of this, and then the bottom second from the right is one also. It's a van and a drone from a company called Workhorse that's based out of Maryland. And then these other examples here have, usually it's a truck and then a robot or a collection of robots that are driving along the ground. Okay, so that's the idea. You're a truck driver and you have this sort of army of robots or drones that are helping you to make your deliveries. And you'd like to know, how do I compute computing the optimal tour is a very difficult thing, but we're just going to try to perform the same kind of asymptotic analysis for this sort of problem and say, okay, what do these costs look like, or what are the trade-offs, and so on and so forth. So here's a picture here on the left is routing with a single sidekick. So this diagram here at the left that looks like a dragon or something. The thick line, it represents a truck that is leaving that depot, which is that center square. So you've got a truck that is driving along, and then these little the dots there represent customers, and then you've got the little dotted line there, little dashed line or whatever that is, that represents the drone or the sidekick. And so the thick line, again, that's the truck driving along, and this sidekick, this drone, is going back and forth from between the van and these customers. So in this picture here, I'm implicitly assuming that the drone has a capacity of 1, because you can see that every time the drone is always alternating between meeting the truck and then dropping meeting the customer and then going back to the truck. And what else do I want to say about this? Oh yeah, in the title I say truck visits forbidden. That just means you'll notice in this picture here that the truck never visits a customer itself, right? We'll assume that that's a constraint, although we'll relax that in just a moment. But that's what that picture on the left illustrates, that the truck never actually goes to any of these customers. It always sends the drone out to do that instead. And then at the right, I'm trying to sketch what the variables are for this problem. So I've got a formulation written there, which we can talk about in just a moment. So the P's, we'll say, are the customers, which is the customers that you have to visit. And then you have P1 through Pn, so n customers. And you have X1 through Xn, and those are what I'm calling the launch sites. That's when that's the variable, which is when the physical location where the truck decides to release the drone. And so that's a variable. So we have to choose both the sequence, like what order should I drop these packages off in, and then where should I release the drone to drop this package off. And so phi 1 and phi naught are the speeds of so phi naught is the speed of the truck, and phi 1 is the speed of the drone, or the sidekick as I'm calling it. And that's what our optimization problem looks like. So actually, I think, if you don't mind, I think I will do a little bit of sketching here to illustrate where this formulation comes from. So let's bring up this again. Sorry, let me do this and share the notepad. There we go. So what am I talking about here? The idea is like this. You have here, we'll do this. This is customer PI. And so this is going to be the launch point XI. And then I'll say over here, and we'll say customer P. we'll pretend that the TSP order is the same as the order of the customers, which is not necessarily true, but I'll do that for notational simplicity like this. So we'll say what happened. So the truck, here's the drone for no, I'll do the truck first. So the truck is driving along and the truck goes here. And then at this point, the drone gets released and the truck continues to move over to the next launch site like this over here, xi+1. And so as the truck is doing this bit, as the truck is driving from between these 2 points, the drone is going like this, right? The drone is flying over and it's doing this bit there. And then they meet again, the drone picks up another package and flies over like this, and then the other drone flies, the truck drives wherever it needs to go. Sorry, I didn't say other, there's no other drone, there's only one drone here. The truck is moving like that, and so on and so forth. And so in the formulation, well, I'll go back to the slide in a moment. We'll just isolate this little piece here, and we'll say, okay, how long does it take before the truck and the drone are here at xi, and then they get over to xi+1? What is the time for that? Well, the time for the truck, excuse me, the time for the truck is just going to be, so it's 1 over the speed of the truck, that's 1 on phi naught, times just the distance between xi and xi+1. And the time for the drone, it's 1 over phi 1, that's the speed of the drone. And then times what happens? The drone goes from xi to pi, and then it goes from pi to xi+1, like that. And so how long does it take before being at this point, before both of the truck and the drone are at this point until they're both over here? Well, it's the maximum of these two, because you just have to wait for one versus the other. And that is why if you look in the slides now, you'll see the formulation. It's the sum of a maximum of exactly these two things, because you're summing over every customer of the amount of time it takes for the truck and the drone to do this work. And of course, also you have to optimize over the permutation, right? You have to decide the what the sequences you're going to do these things in. Okay, so that's our problem. I've also got a formulation here, which it looks very messy, and I don't have so much time to spend on this, but you could also study this problem when you actually have multiple drones, right? Multiple sidekicks, not just one. And that formulation looks like this big ugly thing I've written here, which has a lot more variables, and it's not a very practical formulation, but I just like to include that to show how one models this sort of thing. And then you can also look at the distinction between the case where the truck is allowed to visit some customers or the truck is not. So this formulation here is the one where the truck is not allowed to visit the other customers. This is one where the truck is, and we'll disregard that. But this is the theorem we're going to prove for this problem. It says if you have, so if phi naught and phi 1 are the speeds of the truck and the drone, and k is fixed. K is the number of sidekicks that you have, the number of drones that you have. And we'll say T sub n is the optimal objective value to this problem, which is, in this case, I've decided to make my objective value to minimize the amount of time till completion. So minimize the amount of time until all of the customers get their packages and the truck is back where it started. Then if all of the inputs, all the customer locations are independent and uniform and random, then there exists a constant where the formula here, formula 1 holds, that the length of the time to complete this task divided by the square root of the number of points approaches this constant, beta sk1, that stands for sidekick 1. And that constant is the range of values is pretty big. We just know it's bigger than 0.13 and less than 3.5. But in any event, we know this constant exists, and it's that constant, and then divided by the square root of this thing in the denominator here, the geometric mean of the truck speed and the speed of the drones. And so we've proven this for the uniform case, and we've proven this kind of formula as well for the non-uniform case down below. So the central point here is that we have a theorem that is similar to one of these BHH theorems about the TSP that we've also managed to prove for this problem here. And the goal of doing this is that we can sort of derive managerial insights, or get some common sense as to how much these kinds of delivery systems we expect to help us. So let's look at how you would prove this. So I'll do the upper bound first. Okay, and there's a lot going on in this picture here. And so for uniform, in fact, here I think I'll sketch this picture too. I'm using my whiteboard a lot more than I thought I would, which is kind of a pleasant surprise. I think if I sketch this, it'll make it clearer than this slide here. And the idea is like this. What you would do is you have your unit square, and you have all of your customers. And the idea is that you would break this square into a collection of smaller rectangles, and the shapes and the areas of those rectangles is something you'd have to think about. You break it into a bunch of rectangles, and then what do you do? Let's say we have let's say there are 4 sidekicks, 4 drones. What I'm sketching in that diagram there is the following idea. So what your truck is going to do, your truck is going to go through these rectangles, and it's going to zigzag through them like this. It's going to go through each of them, and it's going to traverse these rectangles 3 times. And here's why you'd want to do it 3 times. Here's what happens. In each one of these rectangles, the truck moves left and right and left like this, or it moves back and forth over the rectangle 3 times. And here's what happens. As the truck moves this way, the first time it goes through this rectangle, it is releasing the sidekicks as it does that. And so we have 4 drones, so we'd have to set this rectangle up so that there are 4 customers inside it. So you release those drones or sidekicks, and then the truck moves back like this, and then it comes back again, and as it comes back, it has to pick these drones back up. So that's why you have to move back and forth 3 times, because you have to go, once to release them, and then you want to enter the rectangle on one side and leave in the other. So that means 3 times total, an odd number. So you drop them, you release them, and you come back, and you repeat that process everywhere. So that's what I'm trying to convey in that picture there. So for uniformly distributed points, as I write there, we actually can describe a policy wherein the total time looks like square root of n divided by this geometric mean. There's an upper bound for the non-uniform case too. You zigzag in this way as well, but you do kind of a non-uniform sort of stretched out zigzag that looks like that. And so for the lower bound, let's see, I'll have a couple of things to say about this. The main thing that we do to perform a lower bound is identify a much simpler problem. Because if you go back to the original problem there, where did I have it? The problem that I was interested in looking at, there it is. Either one of these, right? This is a big, ugly, messy problem, right? There's a lot of things going on. And so the first thing that we did to sort of attack the lower bound and to try to prove this theorem is to simplify that problem and express it in terms of something, more elementary quantities. And I'm doing that here. And so if you look at this, this is choosing some x's to minimize the maximum of 2 separate things. So I'm choosing my x's, and I want to minimize the maximum of these 2 things here. The first is the TSP tour of these x's, and then divided by the speed. So it's the amount of time for the truck to visit all of these points. And then the other one here is 2 times the sum of the distances between these customers and the x's. And so what I would do here really is I would say that this left hand, I'm taking a maximum of 2 things here. The left hand term represents the total amount of time that the truck is driving, and the right hand term is the total amount of time, more or less, that the drones spend flying around, or that the robots spend driving along. Okay, so the actual derivation of this is not so interesting, but we've got a much simpler problem now that we can prove is a lower bound of our original problem. And so the idea is this: the problem we have a TSP. We're taking a lower bound of our problem, which is the maximum of 2 things. The first of these things is a TSP tour, and we already know how the TSP tour behaves because of this Beardwood-Halton-Hammersley theorem. So we know what the asymptotic behavior is of that. And the thing on the right is the sum of a bunch of distances, and distances to a collection of these xi's. And it turns out that that thing on the right actually looks a lot like the p-medians problem, which I wrote before. That's the problem where you're selecting landmark points to minimize the sum of these distances there. So here's a lemma. The lemma is going to say that if you have a solution to the original problem and it's very good, then that also is going to give you a solution that might be good, it might not. But if you have a solution to your original problem, then that induces a solution for the TSP and for the p-medians problem. And so that's this lower bound here. It says that whatever the optimal objective value is for this lower bounding problem, the following two statements are true. Number one, the TSP TOR is less than or equal to the truck speed plus the number of drones times the speed of the drones times this lower bound. And then as well for the p-medians problem, there's an upper bound that involves that as well. And so what I'm trying to get at here is just that you can express the original problem, this sidekick routing problem, you can express it in terms of a TSP TOR and a solution to the p-medians problem. And by doing so, you can obtain a lower bound. That's what you want it to be. So here we did some numerical experiments to see if these predictions actually worked. So again, we've proven this theorem about how long this TOR is going to be in an asymptotic limit. And so, it's an excruciatingly difficult problem to solve. So Bo Jones, my collaborator, just wrote a kind of local search routine to try to study this. And what we found is that these predictions worked pretty well. The reason I say that here, if you look at these diagrams, this is a plot of the predicted length of the TOR divided by the actual length as measured by this local search process over different values of I'm kind of squinting here because the window looks really small, but different values of K, so different numbers of sidekicks, different drone speed, different truck speed. And the thing that I would want to look at here is that these plots are pretty flat. There is this one little hump that a few of them have when you have when phi1 is very small, meaning when your robots or your sidekicks, your drones are really, really slow. There's a little hump there that happens, but if you disregard that, these plots for the most part are pretty flat, which indicates that this prediction is pretty consistent. So we're pretty happy about that, and we think that it does give you some predictive power as far as determining what the length is going to look like. So that's horsefly routing. A lot of future work to be done in this. I've looked at a pretty simple problem because that's sort of the premise here is that you make the problem as simple as you can. But there's a number of things we want to generalize. We'd like to say, what if the sidekicks can visit more than one customer? Right? Everything about this problem that my analysis has assumed that these sidekicks can only visit one customer. And you could also look at capacities, right? What if the truck has capacities and the truck has to go back to the depot? How does that affect this? Or what if the sidekicks, what if the drones have battery life that is very limited, and so we have to only use it when it's really beneficial for us to do so? I predict that what that would mean is that you'd really only want to use the sidekick in the densest places, but I could be wrong. Maybe you actually want to use the sidekick in the sparsest places because that's where you can use its advantages to the highest. I don't know. So there's a lot of ways that you could generalize this kind of analysis that we're excited to look at. That's topic number one. The second one is joint work with Mohammed Javad Azizi, who's, as I said before, an alumnus of your program. And also actually joint work with Mehdi Barouzi, who is an alumnus of Sharif as well. And this is on what we call selection routing problems. So this is just a term that I wouldn't say I invented it, but it's just we're trying to look for a term for routing problems like traveling salesman or like VRP. We wanted to look at routing problems where you are not required to visit all of the points, where you have to visit a subset of them. So you have a collection of points out there, and for the terms of the problem don't require you to visit everything, but you have to select which points you're going to visit due to whatever the cost function is. So I don't know if there's some other accepted term for this. This is the term that we've been using. Let's see. So an example of this would be the one of a subset TSP. And if you look at this picture here, there's a number of things going on. So I have 24 points drawn there in total, and they're all labeled 1 through 6. So I have 24 points labeled 1 through 6, and each number appears 4 times. And what I've sketched there, so you'll see, and I've got this X4 there, which is circled. You'll see that there's the number 4 appears 4 times, and well, all of the numbers appear 4 times, but X4, for example, is all the points that are labeled with the number 4. And X5 would be all the points that are labeled with number 5, and so forth. And what I've drawn there is the shortest tour that visits one of each number. Right. So this is that we have 6 sets of 4 points each, and we have to visit 1 point from each set. So we don't have to visit all 24 points. We just have to visit 1 from each number. And so the shortest tour looks like what you see there. Why is this useful? Well, human beings are solving this problem all the time, right? When I wake up and I say, okay, I have to go to the bank and the grocery store and the pharmacy, I have a choice of which bank I want to go to. I have a choice of which pharmacy and a choice of which grocery store. And I'm going to, in my head, try to think about the most efficient way to do all of that. So we call it a selection routing problem because it's not just routing, it's also selecting which member of each set you want to visit. And so another example here would be the cardinality constrained TSP. We'll look at that in a minute. It's a variation where you have n points and you just have to visit m of them. And we'll refresh that later. And then the prize collecting TSPs as well, which I think is related to cardinality constrained TSPs, which we may or may not talk about. And the last bullet there, the cumulative TSP, is actually not a selection TSP at all, but it turned out that the analysis that we worked on to derive these results actually enable us to say something useful about the cumulative TSP as well. So the analysis applies to that, and so we thought, well, we may as well include it. So our goal, we'll stick with this one for the time being, the one of a subset TSP. We wanted to try to prove some kind of BHH theorem, again, prove some kind of theorem about the behavior of the one of a subset TSP of this problem here in the limit as n becomes large. So we wanted to do that and say, okay, how does this thing scale? So we know for TSP, it looks like square root of n. We know that for the drone routing problem I just showed a moment ago, it's root n times the geometric mean of the ratio of the two speeds, and so on and so forth. So let's try and prove it for this one. Oh, that's right. But before I do that, I'll give another motivation for this problem. As I said a moment ago, human beings solve this kind of one of a subset problem every day when they're doing their errands. Although the application that we're presently most interested in is on what is called random stow in warehousing. Now, my background is not in warehousing. It's not a field that I know very well, although there's a particular aspect of modern warehousing logistics that I happen to find very interesting. And like I said, I'm not an expert on it, but it's what's called random stow. So what I've written here at the right is a map of an imaginary warehouse with a bunch of different items, which are these different shapes. And so if I have to do an order picking tour, if I work in that warehouse and I have to pick up, what do I have to do here? This is what happens if someone tells me I have to pick up a star and a square and a hexagon and that sort of nuclear symbol there. And that red line there is more or less the shortest tour that accomplishes that. So random stow would be what you get when you take the same warehouse, but you don't organize the items. So you distribute them randomly. Now, when I distributed them randomly, for humans, this is a very undesirable thing, right? Because everything's a big mess. You don't know where anything is. But if you have a centralized WMS, a warehouse management system that keeps track of where all these items are, which is, what Amazon does, what JD.com does, what Alibaba does, you can exploit this because now you can see that tour is quite a bit shorter than the tour that I had before. Right, and it's not so hard to understand why. If these items are distributed randomly, then the more random they are, the more choices you have about where you want to pick these items up, and so the more likely you are that there's some very short tour that has a lot of things that you want. And so a motivating question for this research was just, how much does this policy help? right? Now there's you can see that there's less order picking involved. There's less work to be done there because the tour is shorter. A downside, of course, is that it's harder to stock these shelves because you have to scatter things out everywhere. At least if you're just taking the simplest possible model. So very complicated question, but I think they're at the heart of this kind of problem is this idea of a one of a subset TSP, which is what we wanted to investigate. Let's go here. So, okay, we'll do some math. The way I would attack this problem is we'll do a lower bound first, and actually I really should be doing the upper bound instead first. I think that makes the analysis easier, but I'll start with the lower bound. And you ask yourself, okay, we'll just ask a question about the TSP in general, not even this one of a subset thing. We'll just try and get a tail bound for the traveling salesman problem. And I'll say, what is the probability that a uniformly randomly selected tour is short? So in other words, if I take n points in the unit square and just take a completely random tour through them, and we ask, what does the distribution look on that length? Obviously, that length is going to be terrible because usually it's going to be terrible because there's no reason for it to be good. It's just uniform and random. But we're going to apply the union bound to this and say, okay, well, apply the union bound. You have n factorial different tours, and each one has a low probability of being good. But if you take all n factorial of them, then there's got to be at least one good one. And so you compute sort of there's a what's called a Dirichlet integral that you'd have to compute to work out this bound here that I've written as a lemma, which we don't need to worry about. But this here, the lemma below, is just a tail bound for the length of a TSP tour of a collection of points. So it says the probability that the length of a TSP tour of n points does not exceed some value L, that it's bounded above by this gamma function, so that the gamma n plus 1 in the numerator there is just n factorial, which is union bound, n factorial different choices. And then this other bit here, 2 pi L squared to the n on gamma 2n plus 1, that's an integral that comes from evaluating the probability that a random tour is good, which you're integrating the mass of this probability space. So anyway, this is a lemma here that gives us a bound on the probability that a TSP tour is particularly short, and this is going to be useful to us when we try to study the one of a subset TSP. So there's the proof here, but we won't bother with that. So here is the theorem that we managed to prove, and like I said, Javad is going to present this next week when he does his qualifying exam. So you have in the one of a subset TSP, you have two parameters. You have n sets of points, and we'll say that each point has size k. So in this picture I had here before, we had 6 sets of points because the numbers 1 through 6 are out there, and each of them had a size 4, right? Because each number appears 4 times. So this would be an example of the one of a subset TSP, and we'd say n is equal to 6 and k is equal to 4. And so we'd said, okay, let's look at a limit where you decide to fix k and you let n become large, and we'll look at what the asymptotic behavior of that system is. So my theorem says that if k is fixed and x1 through xn are point sets of size k, and they're all independent, uniform at random, then the length of this tour satisfies these conditions here. So with probability 1, basically what you want to look at here, we've got constants on the left and the right that are between 0.48 and 1.84, and you've got a lim inf and a lim sup, and you've got a length of the tour on the top. And the important thing here is the denominator of these expressions in the middle. It's square root of n on k. Okay, and so what is the significance of this? I'll do my drawing. I'll do my sketch here again really quickly just to emphasize this. I explained before that Beardwood, Halton, Hammersley theorem says that the TSP tour of n points looks like square root of n. Right? I said if I have n points out there and I take this TSP tour of them, that the length looks like square root of n times a constant, right? And this now says one of a subset. This subset problem, which is where you have n sets of k points each, this says that by comparison looks like square root of n on k. So that's the conclusion we want to get from this. It means that, so for example, if k is equal to 4, it means that the one of a subset tor is square root of 4 is 2 is half of the tor that you would get without that. And so that right off the bat tells us a little bit about random stow, right? Because the question I asked when I showed this picture here is, I said, how much work do I save when I go from this policy to this one, right? This is me having, in this picture here, I have 4 choices. For every item here, it appears 4 times. And over here, each item basically appears in the same location, right? I mean, they're spread out a little tiny bit in these shelves, but basically each item is located in the same place. And so this theorem says that in the limit, the difference between this tor and that one is going to look like a factor of 2, because 4 choices, square root of 4 is 2. So that's how that works. And so that's the uniform case. So how do we prove that? Sorry, this is the slide we were on. And so the proof is, it looks like this. For the lower bound, you would apply that union bound lemma I had before. So I had this lemma here that, come on, the bottom pit here, the lemma here that says, here's the probability that the TSP tor is, does not exceed some value L. And then you'd say, well, let's apply the union bound again. And you'd say, look, I've got n sets of k points each. And so how many possible ways are there for me to select n points out of each of these k sets? Well, that's just k to the n. And if you look there in that first equation there on the right-hand side, all I did was multiply that lower bound I had before by k to the n. Okay, so I did the union bound once over n factorial, and now I'm doing it again over k to the n, which is the number of ways of selecting these things. And I say e to the n is the event that the length is less than c times root n on k. And so I've written my probability out here. I've got an inequality involving that. I like to take the log of it. It makes the expression easier. And you can show that this probability goes to 0 provided that c is less than 0.4839, which is just some numerical constant there. So that's how that lower bound works. And for the upper bound, actually, it's pretty simple. As you've seen before, when I'm doing upper bounds for these problems, the thing that I do is I just construct a tor using some method here, and this is no exception to that. For the upper bound, I claim if you just take the farthest right point out of each of these sets, or the farthest left point, or the uppermost point, or whatever you want it to be, if you have n sets of k points, and out of each set you select the point farthest to the right, then the distribution looks like this thing that you see here, and then you apply this Beardwood-Halton-Hammersley theorem to get this result that also has a square root of k on it. So very quickly, that's how that upper bound works. We also managed to prove the non-uniform version of this. This is something I was very, very proud of. We've been working on that non-uniform version of this for at least, I would say, 4 years before finally coming up with something. And so this is the non-uniform version of that theorem. And the difference between the uniform and the non-uniform, if you look at this result here versus this one, is, again, the denominators of these two expressions. And you might remember, so let me bring up I want to just emphasize the main talking point here to convey the central idea. So if you were to go back to my slides on the Beardwood-Halton-Hammersley theorem, remember I said that the TSP looks like square root of n when you have a uniform distribution, and the non-uniform TSP, it looks like square root of n, and then also times the integral of the square root of your distribution function, like that. Okay, and now what this theorem says is that the non-uniform one of a subset TSP, what that looks like is root n, and instead of square root of the density, now it is actually the square root of, and now I have to squint and look at this, the density times a function which I am calling p of x to the power of k minus 1. And there should be a k in there too, I think. I think there should be, but okay, well, there may be, there may not be. I'll take it out for now. I think there is. I'm going to put it in because I think it's there. This thing like that. And what is P of X? P of X is the mass of all of the probability, is the mass of all of the points that are less dense. Oh, sorry, I think I've hidden my window there. It is the mass of all the points that are less dense than the point that you are at. So it's a big ugly there. I actually don't think that helps. I think that's just I think I just written a pretty nasty expression there. But anyway, I guess the point I just want to make is that whereas for the non-uniform TSP, we knew that the square root of the density was an important quantity. For the one of a subset TSP, it's the square root of a sort of a more complicated integral, but we have an expression for it nonetheless. So that's what that is. I'm almost out of time here, so I'll just emphasize the most important points. The cardinality constrained TSP. So this is a problem that we think is useful when you're looking at orienteering problems, for example, or prize collecting problems. Bring up my window one more time, like that. So the cardinality constrained TSP would be a problem that looks like this. Let's say I'm in the unit square again, and I've got 12 points here. So this would be n equals 12, and we'll say you give me m equals 6. The cardinality constrained TSP, I'll call it CCTSP, would be to find the shortest Tor through these 12, the shortest Tor that visits 6 of these points, hence the 6 there. So maybe 1, 2, 3, 4, 5, 6, like that. Okay, so it's also a selection TSP because you don't have to visit everything, but it's different from the one of a subset TSP because you don't have a bunch of sets of points. You're just given a whole bunch of points, and you have to visit, any 6 of them. And so we have a formula for this expression as well. We have an asymptotic expression for the length of this thing for the upper and lower bounds. And again, in the non-uniform, upper and lower bounds and uniform and non-uniform distribution, as you can see what I've written here. I don't want to go over here, so I'll skip over cumulative TSP, which is, as I said, not actually a selection TSP anyway. Here are some computational experiments. Javad's experiments are a lot nicer than mine, and I wish I had thought to include his in my talk. But what these plots show effectively is that the formulas that we've predicted or used to predict these quantities actually work pretty well. And the way I would conclude that is by observing, so the 3 plots at the bottom here represent the ratio of, we did some uniform samples in a square or something, and computed the length of one of a subset TSP Tor. And then we divided that by the prediction that these bounds made. And the reason I would say these are good evidence, or the reason we feel good about our prediction, is the fact that these plots on the bottom don't appear to be moving up or down. They're more or less flat. And so because they're flat, we would conclude that, oh, okay, this prediction is pretty consistent across different numbers of values of n and k and things like that. So I think that will conclude my talk here.